Hello, and welcome to the first video of Math 181, Calculus 2. Before we get started, I'd like to share some advice about how to learn efficiently and effectively in this class. First, if you feel that the videos are going too fast, then remember at any time you can pause the video or replay a part you'd like to watch again. There's no shame in watching reruns. Second, if you feel that the videos are going too slow, then I encourage you to increase the playback speed to 1.5 or 2 times the normal speed. And if you want to hear what I sound like when I just wake up, try changing the speed to 0.5. Only joking. Only joking. Finally, I encourage you to print out blank copies of the notes and fill them out as you watch the videos. This writing will enhance your memory of the concepts and make it easier to jot down key ideas that you want to remember. Now, without further ado, let's get started with our first topic, finding the area between curves. So recall from Math 180 that we were able to find the area under a curve, that is from the curve to the x-axis, by using approximating rectangles. The more rectangles we used, the better the approximation. Here we're going to use the same technique to find the area between two curves. So here in figure 3 we've got two functions, figure 3 in the printed notes at least, f of x and g of x, and our goal will be to find the area between these two functions from x equals a to x equals b. So what we could do is break the interval from a to b into, let's say, 4 subintervals. So it looks something like figure 1. And approximate the area between the curves on each subinterval using rectangles. So here we've got 4 rectangles, 1 for each subinterval from a to b. So the picture would look like, again, figure 1. And if we were able to compute the areas of each of these 4 rectangles and add them all up, that would be an approximation of the area between f and g from x equals a to x equals b. But we can do better. We can take the interval from a to b and chop it into 10 subintervals, and then make 10 rectangles and add up all the areas of those rectangles. So that would look like figure 2. Notice how the rectangles are fitting the true area between these curves a little bit more tightly. They're going to give us a better approximation. And in the limit, as we would do in Math 180, Calculus 1, these area approximations would approach the true area between these two curves from a to b. So let's try to figure out what the algebra would look like if we're trying to pin this down and come up with some formulas that we can come away with. So going back to figure 1, we're looking at the 4 subintervals, so 4 rectangles. Let's focus on that first rectangle and try to figure out what the area of that first rectangle is. So one of the things we can do is take the subinterval and label the x values that are the beginning and ending of each subinterval. So here, instead of a, I'm writing x sub 1. So remember, the sub means the subscript. And then x sub 2, x sub 3, x sub 4, and x sub 5. Those would be the 5 x values that would divide up the 4 subintervals. So if we look at the first rectangle, well, the top and the bottom of the rectangle are determined by the function values of f of x and g of x at x equals x sub 1, x equals a, or x equals x sub 1. So if we look at the height of this rectangle, it's going to be the top function value minus the bottom function value. It'll be the y value up here at the top minus the y value down here at the bottom. So that would be f of x sub 1 minus g of x sub 1. Then for the width of this rectangle, remember that in Math 180 we used delta x to represent the width of each of the rectangles. And once again, in this situation, we're using rectangles that have a constant width. So they're all the same width. They're all delta x in width is what we're going to call it. So then, now that we've got the height of this rectangle, this first rectangle, and the width of this first rectangle, we can multiply them together to get the area of that first rectangle. So the area of the first rectangle is f of x sub 1 minus g of x sub 1 times delta x. So then we could do this for all the remaining rectangles. This one would be, the second rectangle would be the same thing, except we would just have x sub 2's in here. F of x sub 2 minus g of x sub 2 times delta x, and so on. So to sum up, pun intended, we could get the areas of all the rectangles using a summation. It's the sum as I goes from 1 to n, where n here is representing the number of rectangles or the number of subintervals that we chopped our a to b interval into, of f of x sub I, so this is looking at the ith rectangle, minus g of x sub I, and then times delta x. So this is going to add up rectangle number 1, rectangle number 2, rectangle number 3, all the way up to rectangle number n, which in our figure 1 picture would be n equals 4. So this is the sum of the areas of the rectangles. Then, as we remember from our calculus skills, we can take the limit of the sums of the areas of these rectangles as n, the number of rectangles, or the number of subintervals, approaches infinity. And that's going to approach the true area between these two curves, which we represent notationally using the integral symbol, so using a definite integral. So it'll be the integral from a to b, from the start to the end of the interval, of f of x minus g of x dx. So the x sub i's turn into x's, the delta x turns into dx in the limit, and this will represent the true area between these two curves. So we can summarize and say that if f and g are continuous with f of x greater than or equal to g of x, like we had in figure 3, on an interval from a to b, then the area between these two curves is going to be equal to the integral from a to b of f of x minus g of x dx. So we'll head to the notes and talk about the first example. So these are the printed notes for 6.1. And I wanted to point out one more thing before we move on to example 1, which is that in our pictures so far, we've been using left endpoints for each subinterval. Now remember from Math 180, we said we could use left endpoints or right endpoints to plug in to our functions to get the heights of the rectangles. And here we're just using left endpoints, which was a typical way of doing it. And I just wanted to remind you how you find x sub I, what the formula or a formula would be for x sub I if you're using left endpoints. So it would look something like this. If you use left endpoints, right, using left endpoints, it would look like x sub I would be a plus, and then depending on your I, it would be I minus 1 times delta x. So essentially, when I is equal to 1, when you're looking at that first x value, you want to be plugging in a right there, the start of your interval. And that's what happens here. If you plug in I equals 1, there's no delta x added to that. You just get a. But then as I increases, you're going to add another delta x and another delta x, and that's going to skip you from one x value to the next x value, because the x values are a delta x apart from each other. And then the other part of it is how you find delta x, given that you're going to use n rectangles. And the way you do that is take your interval width, which is b minus a, and divide that by the number of subintervals, or the number of rectangles that you want to use, n. That's just a quick reminder. We're not going to really spend a lot of time doing that. I just wanted to remind you guys it's something that you talk about in Math 180 or Calculus 1, and hopefully that rings some bells. So let's turn to example 1. Find the area of the region enclosed by the curves y equals 2 minus x squared and y equals negative x. Okay, so the first thing we're going to do here is try to get a picture of what's going on. And to help us get a picture of what's going on, we're going to find the intersection points between these two curves. Now, one thing is, just to have a general sense, what is the graph of this first function going to roughly look like? So if you said this is a parabola that's opening down and shifted up 2, or with a y-intercept of 2, that would be correct. What about this curve right here, y equals negative x? What kind of a curve is that? So if you said it's a line with slope -1 and y-intercept 0, that would be correct. Main thing is it's some kind of line. Now we can go ahead and start drawing these, but it'll help to know where these curves intersect, because that will help us determine where the start and the end of our region is. It'll help us figure out where our region is pinched off. So let's find those intersection points. Do this here. Intersection points. These are just the points where they intersect, where they touch. So the way we can find intersection points is by plugging these two equations into each other, or when you have them written as functions like they are here with the y solved for. We have y equals a function of x and then y equals a function of x. You can just figure out the intersection points by setting the two functions equal to each other. So setting 2 minus x squared equal to negative x. If we can solve this to find the x value that satisfies this equation, then we found a single x value where both the y value of the first function and the y value of the second function are equal. So one x value and they both have the same y value, that's a point of intersection. That's a place where the two curves are intersecting at that point. So let's solve this equation. We have a little quadratic equation here. I'm going to move this x squared over to the right just to make it positive, and we'll take the 2 along with it. So we'll get positive x squared minus x minus 2. Then we're going to factor. 1, 2, 2 is negative because there's more negative than there is positive, it looks like. And so we've got x equals -1 and x equals 2. Those are the x values of the intersection points. So then if you wanted the y values, you could plug in those x values into either of these two functions. They should give you the same thing, since the y values should be equal at these x values. And probably the y equals negative x is easier to plug in to, so you'd get y equals negative of -1, which is +1, and y equals -2 for the other one. Okay, so let's start to draw a picture of this. I'm going to pause the video just to draw the coordinate system, save a little bit of time. Bing, there's the coordinate system that I just spent about 5 minutes drawing. All right, maybe not 5 minutes. Okay, so let's go ahead and draw our intersection points. So we have x equals -1, y equals 1, that's right here. X equals 2, y equals -2, that's down here. Now we know that on the one, for one of them, we've got this parabola that's opening down and has the vertex, or the y-intercept and the vertex are going to be the same point here, at 0, 2. So we can actually put 0, 2 right here as the vertex of that parabola, and then try to connect these using some kind of nice looking parabola. So this is the y equals 2 minus x squared, and I'll call that the top function, as you'll see in a moment. Because the other function, the y equals -x, will be going through the origin. So that's going to look like this line here. All right, and this is the bottom function, y equals -x. So the curves continue on, actually. So you could, imagine that there's more of the parabola over here and down here, and there's more of the line over here and over here. But the thing is, the only finite region, the region with finite area, is the one that's pinched off by these two intersection points. Over here to the left, there's an infinite area between these two curves, and over here to the right, there's an infinite area between the curves. And so we're not really counting those areas. We're only counting the area that's pinched off by these intersection points. So I'm actually going to erase these other curves here. There. And just focus on this area between the curves between. It looks like x equals -1 and x equals 2. So that looks like our interval that we're interested in. Okay, remember that what we're doing is we're taking this interval, conceptually, we're chopping it up into a bunch of subintervals, and on each subinterval we're raising up a rectangle to approximate the area between these curves on that subinterval, just that one subinterval. So let's draw a sample of one of those rectangles, just to provide a visual reference of what we're doing here. It'll help in the long run. So let's say here's one of the rectangles right here that we're using. One of the approximating rectangles. Something like that. So here, when we have this rectangle for reference, it can remind us that the two things we've got to find are the height of the rectangle, which is going to be the top y value of the rectangle minus the bottom y value. So in this case, that'll be the top function minus the bottom function. And then the width of the rectangle, which starts off as delta x, but we know in the limit it's going to become dx. And what we're going to do is just jump right into the integral, but it'll help to always conceptualize these two things, the height and then times the width, and that'll help you figure out what goes inside of your integral, so you don't forget anything. Okay, so our area will be the integral from the start to the end of our interval. Integral and interval start to sound the same. The interval is from x equals -1 to x equals 2. The integral is this old symbol, our old friend. And we're going to take the top y values, which are given by the function 2 minus x squared, minus the bottom y values, which are given by -x. So that's the height of each of the rectangles, and then the width of each of those infinitely thin rectangles is dx. So let me just write down, this is the top y value, and then minus the bottom y value. Okay. In fact, if you wanted to label that over here in our general area between curves formula, you might call it, you could say this is like top minus bottom. Okay. And that matters because if you do the bottom y value minus the top y value, you're going to start to get negative values that you're adding up, negative heights. That's not exactly what we're looking for. We're looking for the positive area between these two curves. Okay, so let's go ahead and clean up inside the integral first. What we could do is, looks like we can write 2, and then this is going to be plus x over here minus x squared. So rearranging the terms a little bit and cleaning it up. Before we integrate, find our antiderivative. So remember, when we find the antiderivative of 2, of a constant, that constant just picks up a letter of integration, so the variable of integration, so that's going to be 2x. And then the integral, or the antiderivative of x, is going to be like this. Add 1 to the exponent, so you get 2. The exponent was a 1 here, right, that we didn't write. So add 1 to that exponent, and then you divide by that new exponent. So you have x squared over 2. What's the antiderivative of x squared going to be? If you said x cubed over 3, that's correct, or x to the third over 3. Because again, we're going to take the exponent, add 1 to it, and then divide by that new exponent. Now remember that you can always double check your antiderivative by turning right around and taking the derivative of this antiderivative, and hopefully if it works out, then you should get back to this original integrand, as we call it. So take the derivative, in other words, of 2x plus x squared over 2 minus x cubed over 3, and you should get 2 plus x minus x squared. Remember that with derivatives, the power comes down, multiplies down in front, and then you subtract 1 from the exponent, so the 2's would cancel, and you would just get a 1 for a coefficient and a 1 for an exponent when you subtract 1 from the exponent. So it works kind of the opposite operations in the opposite order for derivatives. Okay, so then we want to take this from -1 to 2. I should mention that if you are a little rusty on your integrals, you definitely want to practice some of these basic integrals. I recommend that you maybe flip back through your Calculus 1 textbook, which actually is the same thing as the Calculus 2 textbook. So back to those earlier chapters. Try some of the end of chapter review exercises. I do have some videos for Calculus 1, and you can always contact me and I'll send you those links to those videos. And also just feel free to reach out to me if you have any questions about any particular integral that you're doing. So here to help. All right, so then the fundamental theorem of calculus says, part 2, says that all we have to do is plug in the ends of our interval, plug in the 2, and then put a minus, and then plug in the 1 into this antiderivative that we found, and that turns out to give you the definite integral, the area between the area that we're trying to find here. So here we've got 2 times 2 plus 2 squared over 2 minus 2 cubed over 3. That's plugging in the 2. Then we put a minus. Just write that a little bit better. Put a minus. Then we plug in the -1. So we'll have 2 times -1 plus -1 squared over 2. Oops. Minus -1 cubed over 3. Then from here, it's a bunch of fraction work to try to figure out what's going on. Eventually, you should get something like 9/2. So that's the area between these two curves from, well, x equals -1 to x equals 2. That's the region, the finite region that's enclosed between those two curves. So right here, this is 9/2 square units, whatever the units are. Or you can think it's 4.5 or 4.5 would be the mixed number way of writing it. All right, so we'll continue this in the next video. Thanks for watching, and see you in the next part.